All right, this is what you wrote down yesterday. We talked through the process of and the logic of mathematical induction. Okay, we are going to give a statement involving positive integers n. We are going to make sure that 1 is true. Plug in 1, make sure it's true. Then we're going to assume k and show that it's going to imply k plus 1. And if we can do that, then our formula will be true for all positive integers n. Okay? So, this is what we need to do today. Our first step is going to be to plug in n and verify that our formula is true. I have to see that step. We have to knock over the first domino. Then we're going to move into the k and k plus 1 stuff. So you are going to write the word assume, and then you're going to write the formula in terms of k instead of n. Then we're going to show that the formula for the k plus 1 sum is true by using the fact that the sum of the k plus 1 terms is the sum of the first k terms plus the k plus 1 term. We will know that we've done our job by proving that this is true if we can show that this is piece of k plus 1. Okay, remember, and that's what we practiced in our homework last time. Piece of k plus 1. Once we get to that, then our proof will be complete and we can write a conclusion. Okay? So what I'm going to have you do is we're going to write where we start, and then we're going to write piece of k plus 1. That's where we need to end, and then we'll fill in the rest in between using our algebra. So we're going to go through 2 proofs together, and then I will have you start your homework, and before everyone leaves, you have to get through at least 1, if not 2, depending on time. Before you leave, with me coming and checking to make sure that you did it right. Okay? So, here is our first example. Please write down this formula. We're going to write our proof. the first thing we have to do is prove that this formula is true when we plug in 1. Okay. We have the sum of the sequence 2n minus 1. Okay, so we're going to make sure that that first term equals n squared when we plug in n. Okay, so what is our first term? Okay, and does that equal when we plug in 1 to our formula? Okay, that is our first step. Our second step is, well, a lot of steps, but we are going to assume this formula for k. So we're going to assume that 1 plus 3 plus 5 plus 7 all the way up to 2k minus 1 equals k squared. And we're going to call this, I'm really sorry, S of k. And if this is S of k, then we're going to do some work with S of k plus 1. Now, if we are taking the sum of the first k terms, then we add up all of the numbers when we plug in 1, when we plug in 2, when we plug in 3, all the way up to k. Now, we are looking at the k plus 1 terms. What does that mean? That means we're still plugging in 1, then 2, then 3, then 4, all the way up to 2k, or excuse me, all the way up to k. And then, since this is the k plus 1 sum, we are going to add the next term. So if this is the k term, then we're going to add in the k plus 1 term. So I just plug it into that sequence to get that next term.
Equals k squared.
Okay. We do not know that it equals k squared. However, Gabe, that is what we are trying to work towards. Now, first of all, why did Gabe say k squared? Where's he getting k squared? There we go. Okay. And if we're looking at the k plus 1 sum, what do we want it to equal? K plus 1 squared. Okay? So whatever this is right here, remember this is that piece of k. We're going to take that, rewrite it for k plus 1, and that is going to be where we stop. Okay, so what I highlighted in red just now, the sum of the k terms is k squared, so we want to show that the sum of the k plus 1 terms is k plus 1 squared. Okay, we don't know what this equals yet, so don't write it. We want to have our math get us to here. So, let's rewrite this a little bit to make it look nicer. We have 1 plus 3 plus 5 plus 7 all the way to 2k minus 1. How can we rewrite this right here?
2k plus 1.
Okay. Now, I am going to underline something in green. What I just underlined in green, do we know anything about that? What do we know about it?
It's the same sequence as in S of K.
Okay, this is the S of K sum, isn't it? And we assumed that that S of K sum was equal to K squared. So what we can do is we can use our substitution skills, and we can say that this sum is K squared. And then we add the 2K plus 1, that K plus 1 term. Okay. Now, we know the answer that we're trying to get to. How can we go from K squared plus 2K plus 1 to K plus 1, the quantity squared? Okay, say it out loud. Factor it out, right? Okay. K squared plus 2K plus 1 is K plus 1 times K plus 1. And ladies and gentlemen, we made it. We took the K sum that equals K squared, and we showed that the K plus 1 sum was the K plus 1 squared. So, now that we've gone through both steps of that mathematical induction, we can conclude that 1 plus 3 plus 5 plus 7 all the way to 2k minus 2n minus 1 equals n squared is true for all positive integers. And I do want you to write that conclusion statement. I want you to actually recognize what it is that you proved. Okay. What questions do you have? Your question is, are we going to do another example? Of course we're going to do another example. Then he gave.
Are you ready?
Okay. No questions right now. Was it as scary as you thought? No. Really? We wrote more algebra than we did words and symbols, okay? It's really an algebra problem, okay? Now, let me be clear. All of this is your answer. And I need to see that your work logically makes sense from step to step to step. Somebody who doesn't know mathematical induction should be able to read your work and understand what is happening, okay? If your work is not logical, then you are not going to get full credit for your proof. I don't care if you got to here. If you fudge your work to make it work, that's not okay. Everything needs to be mathematical and logical. Go ahead and write this one down. We'll get through the setup at least before we go to lunch. Connor, what's our very first step?
Assume that S1 plus 1. Oh,
Okay, so the sum of the first one term. What is our first term? 5. Does that equal when we plug in 1 to our formula? So 1 times 1 plus 4. Does that work? Yes. 5 equals 5. We are good to go. Our second step, Kelsey. Okay, we need to start by assuming what? Okay, we need to assume, and I expect you to write that word. Assume it is true for k. So S of k is 5 plus 7 plus 9 plus blah, 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 all the way until 3 plus 2k. And we're going to assume that that equals k times k plus 4. That's the only time you get to put the equal sign for our formula in our proof. So when we switch it to k, k is kind of representing any particular value, and then like k plus 1 would be that next value, where n is representing all positive integers, 1 to infinity. Okay, and so by using k, we're like picking a specific domino to make sure that it's going to knock over the next one. Does that make sense? Okay. All right, so if the sum of the k terms equals this, then we need to look at the sum of the k plus 1 terms. And I think that stopping right here would be best, so that when we come back from lunch, we can write out what this means. Okay? So I will see you in a half hour. Okay, so we assumed that the formula for the k sum equals k times k plus 4. Now, when we talk about the k plus 1 sum, that means we're summing up the first k plus 1 term. So we're going to have the first k terms, that's the k sum, and then we're going to add the k plus 1 term. So take this and punch in k plus 1 instead of k. Let's go ahead and figure out what we are working towards. If our k sum equals k times k plus 4, what do we want our k plus 1 sum to equal? Will, what do you think? Can you tell me where you're getting the square?
Oh,
Okay, if this is the k sum, what is the k plus 1 sum? What did you do yesterday in your homework?
You plug in k for k plus 1 for k.
Okay, can you do that for that right here?
K plus 5 or k plus 1.
Okay, that is what we are working towards. Whatever your formula equals, replace k with k plus 1, write it down here. Now we need to get from this to this, logically. So, what I'd like you to do is rewrite this so that we can kind of distribute that k plus 1 through. So 3 times the quantity 2k plus 1 is the same as what? What? Okay. What I am underlining in green, do we know anything about that? Okay, we know it is this right here. So I can take 5 plus 7 plus 9 all the way up to 3 plus 2k, and we already assumed that it equals k times k plus 4. So we just took the sum of our sequence of the first k term, and we knew that it was k times k plus 4, so we just replaced it. Substitution, right? Now I need to somehow figure out a way to get from this to k plus 1 to k plus 5. So what are we probably going to have to do? We're going to need to distribute. So we have k squared plus 4k plus 5 plus 2k. And so then if we combine like terms, we have k squared plus 6k plus 5. K squared plus 6k plus 5 factors to k plus 1 times k plus 5. Yes, Darby?
Is it always going to work out?
The problems that I give you will always work out. Okay, you will not have to worry about that. Now, if you're having trouble getting there, you can't just make up math so that it works. You need to have logical steps, okay? Yes, we did not have to factor to get to k plus 1 to k plus 5, but you need to make sure that if you would factor, it would factor for this. Yes?
When we like, I don't know, like predict what the end thing is supposed to be, can we write that up to the side? Because I don't like running out of space, but I don't like using too much space either.
Yes, that's fine. Okay. What I don't want you to do is say that it equals it right here.
Right.
Okay?
Mm-hmm.
Notice how we say that the k sum equals this, but then when we work with the k plus 1 sum, we are not having it equal anything. We are proving that it equals this here at the bottom. Okay? I just need you to know what to get to. Okay. All right. So then let's write our conclusion. So our formula, 5 plus 7 plus 9, all the way up to 3 plus 2n equals n times n plus 4 is true for all positive integers.
Are we going to have to write down every single one?
Oh yes.
So you can't like skip like the second line to the first line?
Like from here to here?
Yeah.
Now, I would probably be okay with that because I know some of us can distribute and combine like terms in our head, but that would be like the maximum I would let you skip. Okay? To be safe, I would show everything that you can. Okay? What I'd like you to do right now is turn to your neighbor, rock, paper, scissors once. Whoever wins will explain to the other partner each step of this proof. Ready, set, go. Jen, hop over with that. Whoever wins, explain the process.
I want, what?
Here, explain it to me.
You got like, and what you're saying. So you have to approve that. You have all that. The first third is just gonna be five. And then you plug in fourth and that works. Then you can do it. But that is, I don't understand it. And then you have to assume why. Nothing.